Okay, in this lecture we begin to quantify the electric field. We're going to do so using the formal vector notation from Coulomb's law from an earlier lecture. So recall that notation. For example, as a vector, the force on Q due to Q prime is the following expression. KQQ prime times vector capital R divided by the magnitude of that vector cubed, where capital R is the following expression, R minus R prime. Okay, now we always think of the Q as the positive test charge. And then therefore what we're interested in determining is the electric field at some point in space due to Q prime. So then therefore what we do is we take this force on Q due to Q prime and we just divide out by the Q. That then gives us the electric field due to Q prime. The way that we write this is as follows. So the electric field due to Q prime is equal to the force on Q due to Q prime divided by the Q. We just divide out by the test charge. So then therefore we end up with the following expression, KQ prime capital R over R cubed. We of course do have now for the electric field a new quantity, so let's just go ahead and briefly check the units. Okay, so the units very simply are force in newtons divided by charge in coulombs. So then therefore we have newtons per coulomb as the metric SI units of the electric field. And then at this point we go through a simple practice type of problem. What we're going to do in this example is take two fixed charges along a line, find the electric field at the location of one charge due to the other, and then find the force exerted on one charge due to the other. When we do, we'll use this formal vector notation. Okay, let me do a little bit of erasing here before we get to the example. And then just for reference over here, let me write the following expressions. The electric field due to Q prime is KQ prime capital R over R cubed, where once again capital R vector is R minus R prime. And then the force on Q due to Q prime is equal to the test charge Q multiplied by the electric field due to Q prime. That's what we use here as reference. Okay, let's go ahead and access our problem. Okay, we have two fixed charges, a Q1 is equal to -3 microcoulombs. Micro is 10 to the minus 6. And then we have another charge, Q2. This is positive 1 microcoulomb, so 1 times 10 to the minus 6 coulombs. They're separated from each other by a distance of 10 centimeters. I'm going to refer to that distance as A. 10 centimeters is 0.1 meter. Okay, now in part A of the problem, it says, what electric field does each produce at the site of the other? So we actually have to do two calculations here for part A of the example. So here's then how I'll set up the first part of it. Okay, let's go ahead and place the Q1 right here at the origin by definition, and then later on we'll put the Q2 over here at this point in space. But for now, we're going to call this point in space here point P. And the distance from Q1 to point P is the distance A. And now we're going to find the electric field due to Q1 at this location. So E due to Q1. Okay, in order to do so, of course, I have to set up all of my vectors and then get this expression. So first of all, the vector little r. The vector little r always goes from the origin to the point P in space. Because later on in part B of the problem, when we put Q2 at this location, then we'll be talking about the force on Q2 due to Q1. So then therefore little r always goes from the origin to point P in space. In this case, that's of course just A I hat. Okay, and then little r prime. Little r prime always goes from the origin to the charge that causes the field. So Q1 causes the field and it's here at the origin, so then therefore the vector little r prime is equal to 0. Okay, and now we find capital R. Capital R is R minus r prime. So then therefore this is just a I hat, and its magnitude capital R is just a. And now we plug in. So the electric field due to Q1 is going to be K times Q1, and then multiplied by vector capital R, a I hat, divided then by the magnitude of that vector cubed. Like so. Okay, let's go ahead and do a little bit of canceling. Canceling A here and here like so. And then let's go ahead and write the expression like this. Okay, now keep in mind that the Q1 is a negative charge. So then therefore the direction of the electric field at this point in space due to Q1 is going to be a negative I hat. That is to the left-hand side. And that makes sense if Q1 is negative, because recall that the electric field is radially inwards towards a negative charge. Okay, let's go ahead and get this number. Okay, now plugging in. Remember, by the way, that the constant K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. Let's go ahead and plug in. All right, so 9 times 10 to the minus 9, or 9 times 10 to the 9, excuse me. There we go. And then multiplied by Q1, including the negative sign. So times negative 3 times 10 to the minus 6, and then divided by 0.1 squared. And that then comes out to be negative 2.7 times 10 to the 6th I hat newtons per Coulomb. Okay, now let's find the electric field at this position due to Q2, which will be placed over here. The easiest way to describe this is just draw another diagram. Okay, so now here's Q2 at this location in space, a distance a away from the origin, and then the origin is our point P. So now we're going to find the electric field at point P due to Q2. So then we have to write out all of our vectors. First of all, little r. Little r goes from the origin to point P in space. Once again, later on in the problem, we're going to put the Q1 at this location, and then find the force exerted upon it due to Q2. Therefore, little r goes from the origin to point P in space. That's equal to 0 in this case. Okay, little r prime. That goes from the origin to the charge that causes the field. That's just a I hat. Okay, capital R vector is r minus r prime. So that's negative a I hat. And then find the magnitude of that, and then of course is just a. And now we plug in. So the electric field due to Q2 is going to be K times Q2. And then multiplied by vector capital R, negative a I hat, divided by its magnitude cubed. Okay, let's go ahead and cancel out an a, like so, and then we end up with the following expression, like so. Okay, let's make sure that the direction here makes sense. Recall that Q2 is a positive charge. So then therefore the electric field at this point in space due to this charge, that's ultimately then going to be in the negative I hat direction. In other words, right here at this location, the electric field vector will point to the left. That makes sense because this right here is a positive charge. Recall that the electric field is radially outwards from a positive charge. Okay, let's go ahead and get that number. So we now just plug in. So negative, and then 9 times 10 to the 9th. Multiplied then by Q2, 1 times 10 to the minus 6, divided by 0.1 squared. Okay, and that comes out to be negative 900,000. I hat newtons per Coulomb. So notice that the magnitude and directions of the electric fields here and here are completely different from one another. However, what about the forces that one charge exerts upon the other? It should obey Newton's third law, equal and opposite reaction forces. Let's see if that's the case. So now for part B of the problem, let's jump back up to the top board. And now what we're going to do is we're going to put the Q2 right there at that location. And then we're going to find the force exerted upon it due to Q1 by doing the following. So the force on Q2 due to Q1 is equal to Q2 multiplied by the electric field due to Q1. So we take this quantity right here and multiply it by Q2, the positive 1 times 10 to the minus 6. So 1 times 10 to the minus 6, and then multiply that by negative 2.7 times 10 to the 6th. There we go. And this works out to be negative 2.7 I hat newtons. So let's see if that makes sense. If we put the Q2 here and the Q2 is positively charged, the Q1 here and it's negatively charged, the force exerted on this charge due to this should be in the negative I hat direction. And it is. And now here on the bottom board, for part B now here on the bottom board, let's go ahead and put the Q1 right there at the origin. So then therefore the force exerted upon Q1 due to Q2 is the following. So the force on Q1 due to Q2 is equal to Q1 multiplied by the electric field due to Q2. So we take this quantity here and we multiply it by Q1. All right, so negative 900,000, let me just go ahead and type that in first, and then multiply that by Q1, which was negative 3 times 10 to the minus 6. Punching it out, and sure enough, I'll put the plus sign there for emphasis, positive 2.7 I hat newtons. Once again, this in terms of newtons, we're talking about a force. Okay, does this make sense? Sure it does, in terms of equal and opposite reaction pairs from Newton's third law, but you could also, of course, think of it in the following way. This charge here, Q2, recall, is positive. This charge here, Q1, is negative. So then therefore the force exerted on this due to this should be in the positive I hat direction. Positive I hat direction, like so. So once again, you just follow the recipe, if you will, of the vector notation, and that then tells you ultimately what happens.